In our last video, I showed this example, and we chose a specific value for epsilon. We chose epsilon to be equal to 1, and then we looked at what values or what conditions delta would have to be in order to guarantee that that relationship would be true. We're going to extend this to all values and be a little bit more formal in our approach, and then return to our example to kind of highlight the connections being made between the two. Okay, so this is the limit we want to show that as x approaches 9, the square root of x minus 5, the limit is equal to 2. Okay, just to highlight a couple of things, this is our point we were calling C. This bit right here is obviously our f of x. And this part right here is the limit L that we're looking. Okay. All right. So then we want to formalize our proof. Okay. So we'll try to do that. Okay. So we're going to say given an epsilon greater than 0, okay, then we can choose delta equal to something. Okay, so we're going to find out what that something is as we kind of go through this process. And then we'll come back and formalize or finalize this whole approach. Okay, so that's what we're going to try and do. Okay. All right. So suppose that we have 0 is less than the absolute value of x minus 9 is less than delta. Okay. So this is the formal statement of the definition of the limit. Okay, so this is the wiggling in the distance around the x value that we're taking the limit, x minus c. Okay, suppose that that's true. Okay, let's check, make sure that this value is accurate or that it's possible with our f of x. Okay, so we're going to say the absolute value of f of x minus L, which is equal to, I'm just writing this so that we're clear on what it is, the square root of x minus 5 minus 2. Okay, this is the f of x, this is our limit. Okay, and now we're going to do a little bit of algebra. We have to work it back to get it into this form. Okay, that's what we're going to, that's the name of the game. We're going to try to connect to see that this is true, that there is such a delta that exists. Okay, so an unmotivated trick is to multiply by the conjugate of this value, which is really just a little aside for this motivation of the trick. We know that a minus b times a plus b is equal to a squared minus b squared. Okay, so this difference of squares formula is factorable as it's the sum and difference of the two quantities, where the middle terms cross or cancel out in the situation. So we're going to say a is equal to the square root of x minus 5, and the b term is equal to 2. Okay. And the reason why that's really nice is because then the square is going to undo the square root, and so that will free that or allow us to be able to. Okay. So I'm going to rewrite this as x minus 5 minus 2 over 1, and I'm multiplying it by the square root of x minus 5 plus 2, square root of x plus 5 plus 2. And then I'll close the absolute value there. Okay. So notice that this is multiplied by 1, and then I can factor it out just like I did here. But the a, so it's right now it's in this factored form. So the result of this product is going to put it in this form. Okay. So this is equal to, give a little more room, this is equal to the absolute value. And then I'll write it out a little bit slower so it's clear where everything's coming from. Okay, so that's the product of the two things. That's the a squared and the b squared, the a squared and the b squared. And then I'll just notice rewriting the bottom part. X plus, what's that plus? That's minus 5, sorry. Plus 2. Okay. So then simplifying this out just a little bit more, you get x minus 5 minus 4 over the square root of x plus, not plus, I keep wanting to write plus there, plus 2. Okay. Notice that this becomes x, you have the value of x minus 9. And right now I'm moving the absolute value to top and bottom. Absolute value of the square root of x minus 5 plus 2. Okay. So if you notice, this x minus 9, that is exactly what we're looking for. So that's a really good sign that we're on the right track. And then there's one more thing to notice here. Note that the square root of x minus 5 plus 2, okay, for the domain of this function f of x, okay, where x is greater than 5, implies that the square root of x minus 5 plus 2 is going to be always greater than, strictly greater than 1, because this is always greater than 0, and adding 2 to it, right? 2 is bigger than 1, then we're adding a positive number to it. So this is always going to be bigger than 1, which allows us to put a bound on this value here. Namely, since this is always greater than 1, then this thing by itself will always be bigger than, let me say it this way. This thing, x, absolute value of x plus 9, will always be bigger than, if I'm dividing by a number bigger than 1. Okay? So, absolute value of x minus 9 over the square root of x plus, not plus 5, minus 5 plus 2. Oh, well. Let's see if I can write that. X minus 9 square root of x minus 5 plus 2 is going to always be strictly less than x minus 9. Okay. All right. So now that we have this condition here, so we started with this, and we ended up with this x minus 9, the absolute value of that. Okay. Well, we want that to be equal to delta, and we want to show that that's actually going to be true for any epsilon. So how do we choose? Well, we want this to equal epsilon, since it's less than delta. Okay, we have that this is less than delta, so that's where this is coming from. So if we choose delta equal to epsilon, okay, then we will have exactly what we want. So that goes back up here, and that tells us then that we want to choose delta equal to epsilon. Okay, and so if we make that true, then this statement is in fact true. And that's exactly what we wanted to show, which is that this statement is less than epsilon. So just rewriting it to confirm that 0 less than x minus 9 is less than delta whenever the absolute value of f of x minus L is less than epsilon. Or another way of saying that is, specifically to our case, the square root of x minus 5 minus 2 is less than epsilon. Okay. This signifies that we're done with it. So this is true whenever we choose epsilon equal to delta, that is true. And so if we look back at our function here, notice that we had chose that the distance between them, right? We chose the minimum of the two, guaranteeing us that this is true. And so going back to this idea that this is a distance that we're trying to figure out, this comparison, it's saying that whenever we move a little bit in this direction, right, there should always be a corresponding x value. So we move a little bit in this direction, meaning along the function here, right? Moving in this direction means that we're actually wiggling in the y direction, right? So we just want to see if the sequence of points as we move along, is it tending towards the value? Does that distance get, so let's kind of look at a sequence of points and notice what's happening, right? As we cruise along. you can see that the values are tending towards the functional value at, remember, we're taking the limit here at x equals 9, and this y equals 2 is our limit value. Okay, and so as we move along, we're getting closer and closer from either direction. We're tending towards this value, which is exactly what we would have expected given that we found for any epsilon, right? We just choose epsilon equal to delta. You can see that, and so they're getting so close, and it's only, a 20th off, right? That's pretty close. And so they're just going. So it doesn't necessarily mean that this f of x has to be defined at this point, but as we're getting closer and closer, and you'll notice here, this is in the previous video, we chose epsilon equal to 1, and we got a delta equal to 3, okay? So any delta would work. In fact, if we chose delta equal to epsilon, kind of going to that point, like when delta gets to 1, look, these two are equal, and that one also shows that it works. So here, that's 1.1. Let me make it 1. Okay, so in fact, it is exactly equal to. So you'll notice that our delta box here corresponds exactly to the epsilon box. So our delta that we found for 3 works. And like I said, it can be any value as long as we can find a delta that corresponds to it. So we found delta equal to 3 worked, and now with a direct approach, with a little bit of algebraic fanciness, we found another value that works explicitly. All right. With that being said, I just wanted to kind of give a little bit more connection to this idea. And I'll do one more video on this in relationship to this idea being about functions. Okay. I hope that was helpful, and I'll see you in the next video.